We know that a chord other than the diameter of a circle divides the circle into major and minor arcs. Let's say that segment PQ is a chord in this circle. Now, we'll draw another chord RS so that it is equal to chord PQ. Is one of the arcs, say minor arc, made by chord PQ equal to the minor arc made by chord RS? Let's find out. We will take a copy of minor arc PQ and superimpose it on the corresponding minor arc made by chord RS. Observe that these two arcs cover each other exactly and so are congruent. In the same way, we can also show that the major arcs formed by equal chords PQ and RS are congruent. Hence, we can say that if two chords of a circle are equal, then their corresponding arcs are congruent. Now, is the converse of this statement true? Let's see. In this circle, observe that the two arcs AB and CD superimpose each other and therefore they are congruent to each other. Let's find out if the corresponding chords of these arcs are equal in length. Yes, both the chords are of equal length. Thus, the converse of this property can be stated as, if two arcs are congruent, then their corresponding chords are equal. Therefore, in this circle, minor arcs AB and CD are congruent and consequently, the chords AB and CD are equal too. Now, from the center of the same circle, let's draw radii OA, OB, OC and OD. Here, the chord AB subtends angle AOB at the center, and the chord CD subtends angle COD at the center. We know that equal chords subtend equal angles at the center. Therefore, angle AOB and angle COD are equal. Observe that angle AOB subtended by chord AB is the same as the angle subtended by minor arc AB at the center. Similarly, angle COD subtended by chord CD at the center is the same as the angle subtended by minor arc CD at the center. Therefore, the minor arcs AB and CD also subtend the angles AOB and COD respectively. Thus, we can say that equal arcs or congruent arcs subtend equal angles at the center. Angle subtended by an arc at the center is double the angle subtended by it at any point on the remaining part of the circle. We are given an arc AB that subtends angle AOB at the center and angle ACB at any point on the circle. Let's consider three different cases. One where arc AB is a minor arc, the second where arc AB is a semicircle, and third where arc AB is a major arc. We have to prove that the angle AOB is twice the measure of angle ACB in all the three cases. Let us join AB. Similarly, we join CO and extend CO to a point D. Consider the first case where arc AB is the minor arc. In triangle AOC, OA and OC are the radii of the same circle and therefore they are equal. Angles opposite equal sides of a triangle are equal and thus angle OAC is equal to the angle OCA. In triangle AOC, the exterior angle AOD is equal to the sum of the interior angles OAC and OCA. From steps 1 and 2, we can say angle AOD is twice the angle OCA. Similarly, in triangle BOC, we can prove that the exterior angle BOD is twice angle OCB. Now, on adding the equation, we get the sum of angles to twice the sum of angles OCA and OCB. Observe that angle AOD and BOD form angle AOB, and the sum of angles OCA and OCB is equal to angle ACB. Hence, angle AOB is twice angle ACB. Similarly, in the second case, where arc AB is a semicircle, we can follow the same steps to prove that angle AOB is twice angle ACB. Now, consider the third case, where arc AB is a major arc. The angle subtended at the center by arc AB is a reflex angle. We can use the same proof to prove that the sum of angles AOD and BOD is equal to twice the sum of angles OCA and OCB. Here, angles AOD and BOD form reflex angle AOB, and hence reflex angle AOB is twice angle ACB. Let's prove that an angle in a semicircle is a right angle. It is given that AB is a diameter of a circle and angle ACB is an angle in a semicircle. We have to prove that angle ACB is 90 degrees. We know that an angle subtended by an arc at the center is twice the angle subtended by the arc at any point on the remaining part of the circle. Thus, angle AOB is twice angle ACB. As the diameter AB is a straight line, angle AOB is 180 degrees. So, from step 1 and 2, we can say that angle ACB is 90 degrees. And hence, it is proved that an angle in a semicircle is a right angle. Angles in the same segment of a circle are equal. It is given that AB is a chord in a circle. Angle ACB and angle ADB made by the arc AB lie in the same segment ACDB of a circle. There are three cases. One, where ACDB is a major segment. Second, where ACDB is a semicircle. And third, where ACDB is a minor segment. Let's take the first case, where ACDB is the major segment. We will prove that the two angles ACB and ADB are equal. Let us join OA and OB. As the angle subtended by an arc at the center of a circle is twice the angle subtended by the arc at any point on the remaining part of the circle, angle AOB is twice angle ACB as well as twice angle ADB. From step 1, we get twice the angle ACB is equal to twice the angle ADB. This implies that angle ACB is equal to the angle ADB. Hence, we have proved for this case that angles in the same segment of a circle are equal. Let's take the second case, where ACDB is a semicircle. We know that an angle in a semicircle is a right angle. Angle ACB and angle ADB both lie in a semicircle. Therefore, angle ACB and angle ADB measure 90 degrees each. From step 4, both angles are equal to each other. Hence, proved. Now, let's consider a third case, where ACDB is a minor segment. First, join OA and OB. We know that angle subtended by arc AB at the center of a circle is twice the angle subtended by arc AB at any point on the remaining part of the circle. Therefore, reflex angle AOB is twice angle ACB. Similarly, reflex angle AOB is twice angle ADB. This means that twice the angle ACB is equal to twice the angle ADB. In other words, angle ACB is equal to angle ADB. Hence it is proved that the angles in the same segment of a circle are equal. Let's now see the converse of this theorem. If a line segment joining two points subtends equal angles at two other points lying on the same side of the line containing the line segment, the 4 points lie on the same circle, that is, they are concyclic. It is given that AB is a line segment and C and D are 2 points which lie on the same side of the line segment AB. It is also given that the angles ADB and ACB are equal to each other. We have to prove that points A, B, C, and D are concyclic. Let's suppose that 4 points A, B, C, and D are not concyclic, and that the point C does not lie on the circle. Then, C will either lie inside the circle or outside the circle. Let's consider both the cases. Let's draw a circle through 3 non-collinear points A, B, and D. Label a point E on AC such that points A, B, D, and E lie on the same circle. It is given that the angles ADB and ACB are equal to each other. Further, we know that the angles in the same segment are equal. Therefore, angle ADB is equal to the angle AEB. From steps 1 and 2, angle ACB is equal to the angle AEB. However, an exterior angle of a triangle can never be equal to its interior opposite angle. Therefore, our supposition is wrong, and hence points A, B, C, and D are concyclic. Find the value of x. Since angle BAC and BDC lie in the same segment, they are equal. Therefore, angle BDC is equal to 30 degrees. We know that the sum of the measures of all angles in a triangle is 180 degrees. Therefore, in triangle BCD, sum of angles CBD, BCD, and BDC is 180 degrees. Thus, on substituting the values, we find the value of x.